All right. So today we're finally going to cover what happens when we call model.fit, which we've been pushing off for a while because we wanted to get the big picture, and now we can start diving deep. So to motivate this, when you write scikit-learn, you do all this stuff, and eventually you call model, where model is your model object.fit, and you write X train, and you pass Y train. The model learns. We've never learned actually what happens when we call this. So today is all about what happens when we call model.fit. Now, this isn't every machine learning model that we're going to learn in this class, but this includes specifically linear and logistic and other types of regressions. It also includes neural networks, which we'll learn about, but that's what powers deep learning, which is what everyone uses these days, and a few other models, but it doesn't work for every single type of model. And so what happens, how we actually learn the values of our parameters, let's first draw it pictorially, what the process looks like. So let's go back to a data set to reorient ourselves. Let's see.
You capitalize the X for X trait, but the Y for Y trait is lowercase.
It's mathematically because X is a matrix and Y is a vector, but we're not there. We didn't cover linear algebra yet, so don't worry about it for now. But that's the reason why. So what we do is just guess values of the parameters. So maybe we will start with, and this is logistic regression, so we're trying to find a line of best fit. We might start there. And in iteration 0, we just randomly chose parameters such that this was the line of separation. And we say, oh, that's not so good. It kind of classifies everything as one thing and nothing as the other. So then we update the line and see. I kind of just drew this really quick. This one happened to be a good line of best fit. So actually, let me erase that because it's not a good example if it works right away. Just trying to have fun. I just did whoop, but it was a perfect line. So let's be a little bit more careful. And we update the parameters, and now in iteration 1, we get that line of separation, which does better. It's classifying some of the blue points correctly, all of the green points correctly, but it's also misclassifying some of the blue points. So we try again. We intelligently update our parameters, getting closer, and then maybe on iteration 3, we finally found a separating boundary that separates all our points in the training set, and then we can stop. So conceptually, that's what we're doing. We're basically iteratively guessing the parameters, but in an intelligent way, which we'll discuss soon. And once we finally have found parameters for the model that work really well, then we stop. Make sense? Yes?
Sorry, so one iteration is like uses all the data points, right? Like is like each iteration just one data point that updates the line?
There's different variations of it. We'll talk about that. That's later today, not in a different class. Yes?
Oh, this is just linear regression?
This is logistic regression because it's a line of separation rather than a line of best fit. But you can do this for linear regression too. So I don't know, we can maybe so x1, x2, that's how we know its classification. But let's say we were doing linear regression, we might start, these might be our data points. Let's do linear regression just for simplicity. So we might start like that, and then we slowly update it, and then finally it's good eventually. So I don't know, iter 0, what did I draw second? This one, iteration 1. This is not really a line that I drew, but it is. Iteration 2, then iteration 3, stop. We finally found a line of best fit. How do we know that it's a nice line? Well, the mean squared error, which we've talked about, is low. Or in the case of logistic regression, the loss function we use for logistic regression, which we'll learn about later, is low, but it's not mean squared error. We need to cover probability, which I think we'll do either at the end of this class if we have time, or on Tuesday, and then we'll go into the loss function for logistic regression. But we're minimizing some loss for logistic regression, specifically mean squared error loss for linear regression. So that's the high level. So let me just throw you in the water with the concrete steps of gradient descent at a high level. So I guess it's not really throwing you in the water because it'll still be at a high level, but let me give you the algorithm for gradient descent. So step 1 is to randomly initialize our parameters. So I think we've used theta enough for parameters. I can start using that, and you know what I mean? Is that clear? Okay, cool. So that's the nice thing about convention, is that once you use it enough, you don't have to write as much. Second step is calculate the loss with the current parameter values. So with the current set of parameters. Step 3 is update the parameters in the direction of lower loss using calculus, and specifically we'll use the calculus we talked about prior to all the coding classes, where we're the minimum is where you set the derivative to 0. We'll use that intuition here. And then step 4, return to step 2 unless, so used to typing that I forget how to write sometimes. Unless stopping criteria are met. And those stopping criteria could be things like the loss function is low enough so you can just stop, or it can be the number of iterations that you've run, or it can be some other criteria. But that's the idea of gradient descent. Any questions at this high level? Probably not, because it's so high level. So let me go into some intuition as to why we do this, and in particular, intuition about step 3, because I think hopefully is step 1, 2, and 4 clear to everyone. We choose the random parameters, we calculate our loss, and somehow we update those parameters to have lower loss, which we'll cover the intuition for how that works, and then we just keep looping and doing that until like our loss is low enough, or if we've run enough iterations, basically until we're happy with our answer. So we good on that level? Okay. So digging into step 3, which is a little bit mysterious right now using calculus, let's look at some intuition as to how this works. And let's call this intuition on step 3. So I'm going to draw a curve that looks like many types of curves that we're going to see in this class. Where the x-axis is the parameter value, and usually, so this is in the case where you only have one parameter. Usually your model has many parameters, y equals m1 x1 plus m2 x2 plus b. Just with 2 inputs, you have 3 parameters, so it would be a 4-dimensional plot, 3 of these axes, and then a 4th axis showing our loss or our error. And we've seen this type of plot in this class before, right? So you're familiar with this? Good. We're going to see this a lot in the class. And we might have a landscape that we don't know in advance, and this is an important thing to note, where given different parameter values that we choose, we would end up with this corresponding value of loss. And the thing is, we don't know this shape and landscape in advance. If we knew that, then we can just be like, oh yeah, let's go to where the loss is minimum and call it a day and we're done. But we don't know that. So we have to guess different values of our parameter that will get us towards here. This is where we want to go. So let me just label this to be super clear. And maybe I will say we want this parameter value. Should I write out y, or is it clear? Because y'all end up looking at these notes.
Minimize the loss.
Okay. We want this parameter value because it minimizes the loss. Okay. So importantly, we don't understand this loss landscape, but what we do know is that if we choose any particular parameter value, and let's look at a few specific cases. So let's look at what happens if we choose a parameter value here versus here versus here and versus here. These are parameter values that we might have randomly chosen. Fortunately, calculus gives us a beautiful, beautiful tool in our toolkit such that even if we don't know exactly where the minimum is, and we don't even know this landscape, if we take the derivative or the slope of the tangent line at whatever parameter value we happen to have chosen, then we know which direction we would need to go in order to get closer to the minimum value. That's the beauty of calculus, that even though we don't know the function, we don't know where the minimum is, calculus via derivatives lets us know which direction we need to move in. And that's, calculus has many beautiful things that it allows us to do. This is one of the nice tricks that allows us to do. So in particular, if we look at this case here on the right, this is a situation where we have a large positive slope of the tangent line. Here we have a small positive slope. Here we have a small negative slope. And here we have a large negative slope. So we will, when the slope is positive, we want to move left. And when the slope is negative, we want to move right. And calculus lets us know that. So in other words, when the slope is positive, we want to decrease our parameter value. When the slope is negative, we want to increase our parameter value. Any questions on that? Isn't that really cool that like you can figure out your parameter values? And yeah, so that's kind of the central trick of learning, of machine learning, that calculus lets us to do. There's many other tricks, but this is one cool trick. So specifically, we want to move in the direction opposite of the gradient, where the gradient is just a generalization of the derivative at a point, but with multiple variables. So, we can just draw this out with multiple variables just to make that clear. So here's just a pictorial example with, x1, sorry, not x1, parameter value 1, parameter value 2, and loss. And this is just an illustration, just so don't worry about exactly how I'm drawing it, but we have that type of thing, and it goes down this 3D function, and I kind of want to redraw this actually. Sorry. I want to draw it 3D. It doesn't look too 3D. I'm going to draw the same thing, but slightly better. Oop. So loss, parameter value 2, parameter value 1, and let's just draw it like that, so it's kind of clear that we can kind of see where the loss is lower pictorially, even though this is an abstract picture. So we want to move in the direction that's towards there. So that's moving in the direction opposite of the gradient at any given point. Okay, does that sound good? Okay, so specifically, do we have an equation for how the parameters are updated? Yes, we do. So the equation for how the parameters are updated is that our parameter values and specifically our parameter value at time I+1 and the jth parameter value, because we could have multiple parameter values, so we're doing 2 indices, just like you would if you have a nested for loop. So one index on the iteration and the j index on the number of the parameter that you're at is equal to the parameter value at the previous time step. So that same parameter value at that previous time step minus, because we want to move in the direction opposite of the gradient, as we saw pictorially, of some hyperparameter called alpha, which is another hyperparameter, new one, basically the partial derivative of the loss function with respect to that jth parameter. And so that's kind of the central equation of gradient descent, or you could think of it as the central equation of machine learning. I don't think people call it that, they just call it gradient descent, but that's what it is. Where, just to be thorough, theta of I sub j equals parameter j at iteration or time step, however you want to think about it, I. And let's just label this a little bit so it's really clear how the central equation relates to what we saw in the picture. So this is the direction of the gradient. This is because we want to move in the opposite direction of the gradient. And let me add some more room to annotate this a little more. And this is a hyper, just call it, this affects the regularization, or sorry, not the regularization, the learning rate. It's called the learning rate, and it affects how much we move in each time step. So how much we move at each time step. And just to be complete, let's label the learning rate here. So alpha, people often call this alpha, and in scikit-learn, it's parameterized as alpha. So that's what alpha means in scikit-learn, is the learning rate, which is another hyperparameter. We're slowly learning more hyperparameters in this class. Another hyperparameter. And that's gradient descent. Any questions?
What's the symbol before loss?
Before where?
Loss?
This is a partial derivative sign. Have y'all seen partial derivatives in calculus class? Okay. Any other questions? Yeah.
So how is the loss function calculated? Or how do we find the loss function?
So you define the loss function in advance. So that's one thing. When you're designing a machine learning model, you choose the model. You also select the loss function. And the loss function defines how close is what your model predicts to what the true value is. And that loss function, you can define it differently with different loss functions.
If it's growing up, just
There?
I'm good.
Okay. I think, so this is kind of abstract, so let's work out an example for a linear regression. And so just a forewarning that in this example, and with a lot of kind of specific examples in this class, there's going to be some math. Don't worry about the math. I'm not trying to, don't memorize it. Please don't memorize it unless you're interested in it, then definitely memorize it because I think it's cool. But you don't need to memorize it for this class. This is really just to illustrate how you would calculate this automatically. So let's look at a concrete example of one iteration of gradient descent for linear regression. So example, and let's say we have data set of, let's go back to cancer. So tumor radius on the x-axis, and y-axis we'll change it up. We're not gonna do classification. We're gonna make the y-axis cancer severity, which is now a regression problem because we're saying how bad is the cancer, not just is it bad or is it not bad, but how bad is it? So making this a regression problem. Let's say we have data set that roughly looks like that with 10 points. Let's follow the steps of gradient descent as we outlined above. So, and I'll label each of the steps. So, doop, doop. Okay, step 1 is gonna be to just make our initial guess. And specifically, we made our initial guess y equals 0 x plus 10, where this is theta 0 and this is theta 1. So that's step 1. We just guessed, we could have chosen anything, but we happen to have chosen those values. Sound good? Yes.
So isn't there like a little bit of an art guessing? Because if you get something so far off, it'll take forever to get to the correct value, isn't it?
Yeah, so there is, with data sets that are small enough to where you would use linear or logistic regression, you can just randomly guess, and it really doesn't matter because it's going to converge pretty quickly with modern computers. When we get to deep learning, how you initialize your parameters matters a lot because there's a lot of parameters and it's a giant search space. So once we get to these much larger, more complex models, which we'll get to near the end of this class, it matters a lot and there is a big art to it. But for these small models like linear and logistic regression with small data sets where like what you have in your homework where there's only like 20,000 data points, that's a small data set in machine learning. And there's maybe only 20 columns, that's a tiny data set in machine learning, then it's fine to just guess. Yeah, in machine learning, people use data sets with hundreds of millions of data points. That's where you use deep learning. So if it's small, 20,000, this is fine. Big data is the buzzword. Okay, so that's step 1. Step 2 is, let's scroll back up to remind ourselves, calculate the loss with the current values of our parameters. So step 2, calculate the loss. So we're gonna write, we drew 10 data points here. So I'm gonna write out each of these 10 data points, and I guess I'll throw in a side note while I'm writing this that there's not a homework question on this, but this might be on a smaller scale with less than 10 data points, might be the type of thing you do on an exam, so worth giving you a full worked out example so you can use that on your open notes exam. So we have a radius and severity, and let's say we have the following 10 data points. Any questions while I'm writing all this out? Okay. Oops, 1, 2, 3, 4, 5. Oh, I think I changed this to be only 8, just so we don't have to mind. Right. So I'll make the picture follow that. So we have 8 data points, and so just like when you're in your homework 1, we want to make a prediction, and we could easily see it's easy to make predictions here. The prediction's 10 every time because the equation's y equals 0x plus 10. So this column's pretty easy to fill out. 10, 10, 10, 10, 10, 10, 10, 10. And our square error, I guess let me write this out for you. Square error, which we take the mean of to get mean squared error, would be, can someone tell me what it is for this first data point? 100, yep, because difference between y and y hat is 10, squared is 100. So doing that for the other data points, we get our list of squared errors. And therefore our mean square error, back to this, is, going back to our equation of mean, the mean of the squared error of point I. I'm just writing it differently, but same thing, mean squared error, which if you calculate it out, happens to be 1342.25. So now we've done step 2. We've calculated our loss function for our data, and we see that we have this value of loss, where again, lower loss, ideally we'd have 0 loss, where the difference between y and y hat is 0, and when you square it, it's 0. But nope, we're just guessing 10 every time, so we have pretty large values of the squared errors, and therefore our mean squared error is pretty large. Moving on to step 3. This is the fun part, depending on how you define fun. Then we want to calculate, importantly, the big calculation is getting this gradient, which in this case is just a derivative because it's only one input. So this derivative of the loss function with respect to each of our parameters, and we have 2 parameters, we have m and b. So that I don't confuse myself, I'm gonna just clarify that this is b and this is m. Y equals mx plus b. I'm gonna use that in the examples, just so I'm not like, which one was theta 0 and which one was theta 1.
Well, if I can just write down the square error,
Okay, so we want to calculate this partial derivative. And this is where like the math doesn't really matter. Just like understand that we're, that you can get a derivative of the mean squared error with respect to m, and we want to calculate also, so we want to calculate mean squared error with respect to m and mean squared error with respect to b. So if we recall, how do I make this go away? Oh, okay. Whoa, how'd that get there? Okay. So if we recall, so I'll just put in parentheses, recall that mean squared error has an equation that's intuitive. It's exactly what we would expect it to be. It's the mean of the squared error. So y sub I minus y hat sub I squared. That parentheses because we're closing out the parenthetical statement. So the partial derivative of the mean squared error with respect to m is equal to the partial derivative of so of this thing. I don't want to write it all out actually, just to save time. So is equal to the partial derivative of that with respect to m, which is equal to -2 over n times the summation from I equals 1 to n. Please don't memorize this because it's just a derivative and it's not really important. But in case you're curious, the mean squared error of with respect to m, where your model y hat is mx plus b, turns out to be that, which kind of, if you know derivative rules, makes sense. We're just replacing y hat with mx plus b, and then you put the 2 in the front, and the exponent goes away, and then chain rule, you take the derivative of the inside. So if you know calculus, that's all that is. And this kind of simplifies, actually, that's simple enough. So that's our equation, and we do the same thing for b. So we also want the partial derivative of the mean squared error with respect to b, and that, when you evaluate it out, happens to be -2 over n summation I equals 1 to n of yi minus y hat.
Wait, why is it xi times y? What is that x? Oh, x. Oh, that's the chain rule.
Yep, chain rule.
Okay, sorry.
But you don't need to know like the calculus rules in this class, so nope, not a big deal. So now we have, just please don't memorize this or worry about these details. Just know that that's our, that happens to be what the derivative is, but not a big deal. To know exactly what the values are, because if you have a different loss function, your derivative would be different. And if you had a different equation that was like not mx plus b, but mx cubed plus b, it would be different. And so all those variations, make memorizing these specific equations kind of pointless because there's so many variations to the model. But so just so you know, that's how it is done. And so now plugging in the values from the above table, we get that the partial derivative of the mean squared error with respect to m equals -120.9, and the partial derivative of the mean squared error with respect to b equals -67.5. So then let's say the ML engineer, so that would be you guys and girls, would be engineer, let's say the ML engineer sets alpha to be equal to 0.01. It's kind of like a default alpha value. Then then we could follow this equation up here. So we've calculated this partial derivative. So now we're just going to apply it. The ML engineer set our alpha, set the learning rate, and we calculated the derivative of the loss with respect to each of our theta j's for the M version of theta j and for the B version of theta j. So we're just going to update our estimate of M and B according to this equation. So our new M is going to be our previous M minus the learning rate, which the ML engineer set, of negative, what was it? Negative 120.9, which happens to be 1.209, and our new value of B is equal to the learning rate times negative 67.5, which happens to be 10.675. And so now we have new estimates of M and B. And so after this iteration, so now our new model, or let's call it our updated model, our updated model is y equals 1.209x plus 10.675. And if we plot that out, so going back to our original, going back to this, we originally made this initial guess. So I'm just going to do my best to recreate that plot. So draw this a little bit higher. But 1, 2, 3, 4, 5, 6, 7, 8. We initially started here with y equals 0x plus 10. And after one iteration of gradient descent, this is making it look like it's parallel. It's technically not parallel at that point yet. But after one iteration of gradient descent, we start getting a little bit closer. So y equals 1.209x plus 675. And finally, step 4 is go back to step 2. So repeat for many iterations until, for example, the loss is low, or the number of iterations is too high, or ... You can define when you stop. And that is a worked out example of one iteration of gradient descent for linear regression with one input variable. Any questions? Yeah.
So, like when you go up to when you have del MSE over del M equals to minus 120.9, that one, those two at the top, is that from all 8 rows?
Yes.
You sum up all 8 rows, right?
Yes.
Okay.
Question?
Yeah.
So, if the learning rate is too low, can the model overfit because of that?
That wouldn't be the primary reason why the model overfits. It would be because you have an over-parameterized model. But you might get stuck at a local minimum if you have a non-convex loss function.
So,
Uh,
so you
but we'll talk about that stuff
But it
too.
won't overfit per se. It might just
That one, the low learning rate. So the trade-off, this is a great question. So there are trade-offs between high and low learning rates, and you should think through this, like e.g. for an exam. So like, what would a higher learning rate mean, and what would a lower learning rate mean? And I guess I wasn't planning to put this in the notes, but that's such a great question. Let's add in a small section on that. So what happens if the learning rate is too, let's start with too large. So in that situation, we will have, parameter loss. We'll get in a situation where we start with, say, this parameter value at step 0, and then our alpha is so big that we make giant step sizes, so then we end up way over here at step 1. And then we see, okay, that's bad, we need to go in the other direction, but our alpha is so high that we go all the way, here for step 1, and then that's, too big, we need to increase our parameter value, but our alpha is super large, so we make a giant step to the other way, and we end up there, and we kind of never get to our local minimum. We never get there because the amount that we jump each time is so large, we never have the chance to get down to our minimum, our parameter value that will lead to minimum loss. So that's one situation. What about the other situation? So what happens if alpha is too small? Any thoughts on this? Yeah, exactly. It takes forever. So you'll get where you need to go, but step 1, step 2, step 3, step 4, step 5, step 6. We'll just label this steps 0 through, I don't know, I'm just gonna put an arbitrarily large number. You take a lot of steps and you know which direction you need to go, but you take forever to get there, and therefore many computational resources because you made alpha really small. Now, choosing the right alpha is an art rather than a science. That's something that you would want to use hyperparameter tuning for, which we talked about kind of impromptu, but it's an important concept at the end of last class. Alpha is one of the most important hyperparameters. In fact, in grad school, I was doing this project where I thought everything was right, and I had this model. I was like, this is a great model. Why is it not working? And I tried it for couple weeks, and it turned out I just had the learning rate alpha wrong, and so I just divided that learning rate by 200. And now all of a sudden I had a real model that beat everyone else's model in the field who would ever. So alpha could be the difference between not learning and having a model that is the best in the scientific literature. So it's a very important hyperparameter.
What do you mean you could get stuck at a local minimum? I thought you wanted to get to a local minimum.
You want to get to a local minimum.
But you said you could get stuck, and that was one of the problems.
You get stuck up here, which is away from the local minimum, depending on where you start.
So in step 4, so I understand the concept of you're going through it again, but how do you do you just take the derivative again, or is it, right? Because if you take the derivative of the function, I'm good there, but then if I'm doing step 2 again, it seems like I'm.
So you do, yeah, so you do step 2, but now you have a different value for your parameter. So
Okay.
now I mean, technically, you don't have to take the derivative. You use the derivative
Sure,
equation
sure.
with the new values of m and b.
Got it, okay.
Yeah, if you take the derivative again, you already,
Yeah, you're
it's the
just,
same derivative
like,
equation.
you're stuck
Yeah.
in a cycle, doing the same thing.
Yeah.
And then, just the last piece is like, right when you found M and B,
Mm-hmm.
how did you find that?
Here?
Yeah, like what did you plug in for M and B there?
So I used this central equation of gradient descent, which is, this is how gradient descent works. So you intuitively, you're updating each parameter in the opposite direction of the gradient, multiplied by the learning rate, which tells you how big of the jump you should make.
Yeah, what I think I'm confused by, so I got the first one, but then in B,
So m
yeah,
equals m minus 0.1 times, and then the so
got it, okay.
first theta is the m, second theta is the m, alpha is the 0.01, and that partial derivative is the whatever we calculate.
Okay.
So is that helpful to kind of see a big picture and go into the math? And yeah, okay, cool. Yeah, that's a great question in terms of getting this what's the effect of alpha? Because it's so important. Any other questions? Because this is kind of central. Yes.
So rather than stepping through and changing your values for your parameters, is it possible to find the form of the loss function in some like parameter space and then take the gradient and then find the minimized, like I think if you take the gradient it'll return a vector field. So take the minimized vector.
Yeah, so essentially you're saying, is there an analytical way you can just set the derivative to 0 and find?
As opposed to like iteratively stepping down or stepping up your parameters.
Yeah, great question. So if y'all recall, when we covered calculus in our last writing class, we said, oh wait, you could just find the minimum of functions by setting the derivative equal to 0 and solving. So why can't we just do that here? For linear regression, you can do that. When you start getting models that are more complex than linear regression, it's not solvable algebraically. So yes, you can set the derivative equal to 0. Once you've done that, that's not something that you can solve using algebra or linear algebra or whatever. So I'm kind of going back and forth between covering, there is like these things called the normal equations for linear regression. It's like an exact analytical solution to linear regression, but no one even uses that in practice because it's computationally inefficient when you have a big data set. So people still use gradient descent in that case. So even when there is an analytical solution, people don't even do it. Yeah, so basically that's the reason why it's impossible to set the derivative to 0 and solve for it. And therefore we need techniques like this to
When you say
approximate.
impossible, it means impractical?
No, it's impossible. There's no solution.
In theory, no theoretical solution.
Yeah.
Okay.
Sorry, no analytical, no way to, there is a theoretical solution. There is a solution because we have a convex function. So there is a minimum point, but it's impossible to use algebra to solve for it.
We have to use something really weird.
There's nothing you can do to get it unless you do approximate it. And actually, like, turns out I was kind of mad because when I took differential equations as a class, it's the same thing where like you learn these differential equation rules, but then in the real world, no one does that because all the actually useful differential equations in science are too complicated and you have to approximate it. Same thing here, like when you get to real world things. So you learn all these rules in math classes and then you never actually use them in the real world. And so, I don't know. I mean, still pay attention in math, but just keep that in mind, I guess. Okay. Any other questions on gradient descent?
Are we going to explore like being able to take different step sizes, like say start off with a larger step size and over time just reduce it so we can get a good combination of speed?
Yeah, great question. Yeah, not today, but when we get to neural networks in particular, we'll look at a bunch of variations of gradient descent that allow you to do things, including that, but other things as well. I might just give some intuition today on some of those things, but.
I was more worried about the tools that we're using and how easy it is to change those things. Is it pretty?
Oh, yeah. So I don't think in scikit-learn it's easy. And later in this semester, we'll start learning TensorFlow and PyTorch. Maybe just TensorFlow. I don't want to throw too much at y'all. So just TensorFlow, and there it's really easy to have an adaptive learning rate. So it's one thing you can do is have the alpha change over time. So it either gets usually smaller over time because you start off taking big step sizes, and as you go, you take smaller step sizes. So that's something you can do. Great question. Anything else? And you can imagine all sorts of modifications to this basic paradigm, just like there's all sorts of modifications to y equals mx plus b, and yeah.
But you say that at the very start of the class that this is what happens when we do model.fit
Yep.
on X train and Y train, but there's no input of like an alpha function, for example, in there. So how would that machine learning engineer?
So there is, it's an optional parameter in scikit-learn, usually. Yeah. So it's kind of, there's a default one, but like if you're doing it in the real world, you iterate. And probably for homework too, you should iterate through many potential alpha values and see what works best. If you're using a model that uses gradient descent. Like we're gonna learn things like naive Bayes in a couple classes that doesn't even, it's just a probability, so there's no learning to be done. It's just you look at the data and yeah. Anyway, we'll get there. I don't want to get ahead of myself. Okay. So there's a few gradient descent variants. Gradient descent variance with some trade-offs. So the situation we just talked about that looks at all of the data, all of your training data together is, people like to call it batch gradient descent. It's kind of a lame name, but batch gradient descent, and that means you use all the training data when updating data per iteration. And when you train using batch gradient descent, you tend to get a curve that kind of, I always have to label the axes in this class because we saw what happens when we don't look at this. And there's all sorts of 2D plots we draw. Sometimes X is on the X-axis, Y, but here theta is on the X-axis, loss is on the Y. We tend to get smooth learning. So, oh, sorry, I mislabeled this axis. Speaking of, that's kind of funny. So this is not theta. I was thinking it's not theta, and I wrote theta. This is the number of iterations of gradient descent. So as you run more iterations of gradient descent, your loss goes down, and it's pretty smooth if you look at the entire data set at the same time. But another thing you can do, and we'll talk about the trade-offs of this in a second, is mini batch gradient descent. Where you update your theta using random subsets, mini batches, each iteration, And number iterations loss. When you do this, because you're not looking at the entire data set, every time it kind of has a less, you eventually kind of get near where you want to go, but it never quite fully converges because you're looking at small subsets, so you can see intuitively why that would be the case. You're calculating your loss with respect to the same test data, but you're looking at different subsets of the training data every iteration. And finally, and we'll get to why you would use one or the other. But finally, we have stochastic gradient descent. People often abbreviate this as SGD. So I'll do that here. So when you see SGD, that's what it means. So stochastic gradient descent, which is where you update theta using one data point per iteration. So you just look at one data point. And drawing that out, it basically looks similar to mini batch gradient descent, but more extreme. So why would you use one or the other? So the main con of mini batch gradient descent or stochastic gradient descent is it does not converge. It kind of continuously cycles. So let's use a. So the main con is that it does not converge. Well, pros are that number one, it's faster in each iteration because you're considering a smaller subset of the data. And kind of added benefit is the randomness of this process helps reduce overfitting. Do y'all remember overfitting from a few classes ago? So it helps reduce that. So for stochastic gradient descent, the pros and the cons are the same as mini batch gradient descent, but more extreme. So these are just some variations of gradient descent. Any questions?
Could you go back to the last one?
Are there other versions of it as well?
Are there what?
Other versions of gradient descent as well, or are these the main three?
So these are kind of, I mean, in terms of what proportion of the data set are you looking at each iteration? These are the variations, but there's other variations that you could apply to any of these three. For example, the adaptive learning rate, and there's some fancy things that we'll learn about that don't really apply when you're doing linear and logistic regression because you're optimizing a convex function. So there's always, the local minimum is always the global minimum. But when you get these complex loss functions and models that where you can get stuck, then there's additional modifications to handle that. But you don't need that for linear and logistic regression. You're guaranteed to converge, or if you're doing stochastic or mini batch, cycle near the minimum loss. Yeah.
It says that one of the cons was, or one of the pros was reducing overfitting.
Mm-hmm.
But I thought we
There's many, so one of the big things in machine learning is how do you reduce overfitting? And there's a myriad of techniques to reduce overfitting. This is one thing that might help sometimes.
So it seems like you could also, another strategy is use, I mean, you could still use a hybrid model, but once you get somewhere, you can kind of just bounce around where you are
Yeah.
to see if the overfitting model would just improve in that area.
Yeah, and that's a good stopping criterion, by the way. If you're going back and forth, that's probably a good time to stop gradient descent. Speaking of other stopping criteria in the ... that I listed.
You could also use like a simple model, right, to prevent overfitting.
Yes, so you can start off with a simple model, or you can start with a complex model and give that complex model the freedom to set parameters to 0. That's kind of where I was getting at when I started with regularization, but we will come back to regularization. Actually, is our next topic. Maybe not today, because I don't want to get into a situation where there's 10 minutes left and, again, I rushed through it. So we'll start Tuesday with regularization. There's just a couple more points I do want to cover about gradient descent. And we'll start next class with regularization, and then we'll cover probability. So I'm like slowly throwing math at you, but right now it's just calculus. Hope it's good. And then I'll throw a probability, and then we'll cover a bunch of new things that are probabilistic and things that combine calculus and probability. And then we'll cover a bunch of things using just that. And then we'll add linear algebra much later, and then cover a bunch of things using that. I feel like if I threw all of these things at you at once, it'd be too much. And one of the learning goals of this class is to make math fun. I feel like throwing too much math at you all at once is not making math fun. So I don't know. That's my opinion, though. Okay, so handling non-convexity. Non-convexity. So fortunately, with linear and logistic regression, we're always going to have a convex loss function. So a convex function, formally defined, and this is an important concept in math and in machine learning, is a function is convex if you can draw a line segment between any 2 points for the function, and that line is consistently above all those points. Let me write that out and draw a picture so you see what I mean. So you have a convex function if you can draw a line segment between 2 points that are above the function for all points in between, which kind of sounds mysterious when you write it out, but if you draw it out, it's pretty clear. So for example, this is a convex function. That's like what the loss curves tend to look like. This is a not convex function. And notice for convex, take 2 points, draw a line. That line is above all points between the 2 points that we defined. Whereas we can select 2 points here where there are parts of this function that are above the line, and therefore this is not convex. So the nice thing about a convex function, well, actually, just to be complete, just by the way, kind of a side note, concave function. I'm going to put this all in parentheses. Same, but below line. So for example, this is just because you always hear convex and concave. So that is concave. Okay, just that's a big parenthetical because convexity is really what we care about because we're trying to minimize our loss function. We're not trying to maximize anything besides maybe likelihood, but we will get to that.
Question?
Yes.
So can functions be neither convex nor concave?
Yeah, so for example, this not convex function is neither convex nor concave.
Okay, so convexity is not counted, not inclusive.
Yeah, so not convex or concave. Yeah, it's not either you're convex or concave. You can be convex and you can be concave, but you could also be neither. So in machine learning, in ML, a convex loss function is good because it means that we will approach, I don't want to say find in case you're doing stochastic gradient descent, but it means we will approach the global minimum loss using gradient descent. And unfortunately, the best performing models, which we'll get to, unfortunately, more complex models like neural networks are not convex. And so in a neural network, you might get to a situation where you have, for example, we're back to theta in loss. So going back to those being the labels to the axes, might have a loss function like that. And the problem is that we might start here and then go down here and then go down here and then here and then here, 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 and then say, we're done. We found our minimum, even though this would have been better. This would have been better. So there's a family of solutions to that, which I don't think it's worth covering until we learn neural networks, because right now all the models we know about don't have this issue, but this is just kind of a sneak peek. One of those is called, let's just right there, are many not solutions, but approaches to try to mitigate this. For example, there's something called momentum, which has some math, but it's kind of just intuitive, where you use the history of past values of, or past changes to your parameters to simulate what you would think of as momentum in physics, where like, you know, you have your loss, this will be the last picture, and then we'll be done. Loss, and you know, it's like this, and you could just think of it as like a ball rolling basically downhill, and ball. So like the point you're at is now a ball, and you roll downhill, but because there's momentum, it can kind of slide and go over the hill and get down to the next one. And there's math behind it, but some nice intuition. And that's one example, and then there's many, many, many others, and some that include momentum plus other things like atom optimization. But we'll get there. So that's our class for today. Now you know how models learn. See y'all next week.